The rate of change of the amount of a solute in a mixing problem is the rate of inflow of the solute minus the rate of outflow of the solute. Very obvious. The rate of outflow is the concentration of the solute times the rate of outflow of the solution. Multiply the concentration by the amount of solution you've left, you have the amount of outflow of the solute. And in general, the concentration of the solute in the solution is going to be changing. Okay. The rate of inflow, well, you have a similar statement. It's going to be the concentration of the inflow times the rate of inflow. So, if Q is the amount of solute, R sub N is the rate of inflow, the concentration of the inflow solution is C, and the rate of flow out is R sub out. Container with volume V, what's the rate of change of Q? Well, the rate of change of Q is going to be the rate of inflow minus the rate of outflow. Now, kind of assumed here that you have a constant volume of solution. That is, you've got a container that's full and you've got a rate of inflow that's equal to the rate of outflow. In that case, this would be concentration times rate in minus Q over V times the rate out. Okay? Now I say V is the volume of the container. Better, V is the volume of the solution. Then this holds. And the volume of the solution might be the volume of the container if the container is full. But of course the container might not always be full. So that you have dQ dt equals C times rate in minus the Q over V of T times rate out. In other words, this is the rate and the rate is dQ dt, so this is what we have. And I've got a V of T down here because the volume of the solution might in general be changing. Okay, now, I need to make a modification here. I'm going to let V CONT stand for volume of the container. So here's the volume of the container. Can't really read it, but that volume of the container minus the initial volume. Okay. Then we can say that the volume as a function of T is V naught, which is taken to be the initial volume of the solution, plus the net rate at which solution is flowing in, and that of course would be the rate in minus the rate out, and then you multiply that by the time. Now, if you happen to have a non-constant rate in minus rate out, then you would have to integrate the net rate with respect to time in order to find how much volume has changed. Okay, well, again, assuming we have a constant rate in minus rate out. If V naught is less than the volume of the container, V naught being the initial volume in the container, then the domain of your V of T function would be subject to the condition that V of T is less than or equal to the volume of the container, which means that V naught plus the net rate times T is less than or equal to the volume of the container. And you can solve that for T very easily. And you get T from 0 to volume of the container minus V naught, that's what this incomprehensible numerator says, divided by the net rate.